This video covers the building blocks of statistical learning, mainly around definitions. There's a lot to cover in this video, so let's get started. Before we dive in, here is a quick roadmap of everything this video will cover. We will begin with the basics: input and output variables, how we represent models with formulas, and special kinds of variables like confounding, categorical, and interaction variables, along with transformations. From there, we will explore prediction and inference, including reducible and irreducible error, and compare the two goals side by side. Finally, we will look at parametric and non-parametric methods, the trade-off between flexibility and overfitting, and finish by contrasting supervised versus unsupervised learning and regression versus classification. Let's start with the two types of variables in every statistical learning problem: input variables and output variables. Input variables, also known as predictors, explanatory variables, independent variables, features, or regressors, are the variables that you input into your model. The output variable, also known as the response, the outcome of interest, the dependent variable, or the regressand, is the variable that you are trying to predict or explain. Let's test this with a quick example. Suppose we want to predict a student's final exam score. We are given the following variables: hours of study, attendance rate, number of assignments completed, participation in class, and the final exam score. Which are the inputs and which is the output? The hours of study, attendance rate, number of assignments completed, and participation in class are the input variables. They are the information we feed into the model. The final exam score is the output variable. It is the outcome the model is trying to predict. A common way to represent the relationship between input and output variables is with the following general form: y equals f of x plus epsilon. Y is the output variable, also called the response. x1 through xp are the input variables, or predictors. F of x represents the systematic information that describes the relationship between the inputs and the output. And epsilon is the error term, representing the deviation of the observed values from the true values due to randomness or other factors not captured by f of x. One notation convention to keep in mind: capital X and Y denote the random variables, or the theoretical model, while lowercase x and y refer to observed data points, or specific values. Let's visualize this with a simple linear relationship. The blue line is the true underlying function, f of x equals 5 plus 2x. It has an intercept of 5 and a slope of 2, so for each unit increase in x, y increases by 2 units. The white crosses are the observed data points. Each cross corresponds to a pair of values, xi and yi, for an observation I. Notice that they don't fall exactly on the line, because each observation includes some random noise. The vertical distance from each cross to the blue line is the error term, epsilon I. These errors capture the randomness that causes the observed data points to deviate from the true function. Next, let's talk about confounding variables. A confounding variable is an external variable that affects both the independent variable and the dependent variable, potentially leading to a false association between them. Here's a classic example. Suppose we are studying the relationship between coffee consumption and heart disease. Smoking can act as a confounding variable. People who drink more coffee might also be more likely to smoke, and smoking is a known risk factor for heart disease. If the researcher does not control for smoking, they might incorrectly conclude that coffee consumption directly increases the risk of heart disease. Statistical control involves using statistical techniques to account for potential confounders, so that the effect of the independent variable on the dependent variable is accurately estimated. This can be done through methods such as stratification, matching, or using statistical models to adjust for the confounders. Variables are not always continuous. Let's look at 4 important types of categorical and discrete variables: binary, nominal, ordinal, and count variables. Binary variables represent categorical data with 2 distinct outcomes, typically coded as 0 and 1. They capture the presence or absence of an attribute, event, or condition, such as yes or no responses, or whether an event occurred. Nominal variables categorize data without any intrinsic order, such as blood type or eye color. Ordinal variables not only categorize data, but also rank it in a specific order, reflecting a relative position or degree. Think of satisfaction ratings, from poor to excellent, or education levels. Lastly, count variables quantify the number of occurrences of an event within a fixed period or space, such as the number of customer visits to a store, or the number of emails received per day. Each of these variable types has dedicated regression techniques, which are covered in later videos. One common way to introduce linearity to nonlinear functions in regression models is through transformations of the explanatory variables. Consider the polynomial regression model, y equals 5 plus 2x squared. The relationship between y and x is nonlinear. On the left, plotting y against x gives a curve. However, if we treat x prime equal to x squared as the explanatory variable instead of x, the model becomes linear. On the right, plotting y against x prime gives a straight line, so the model can still be considered a linear model. The same idea works for other functions. Consider y equals 5 plus 2 times the exponential of x. The exponential introduces nonlinearity, but the model is linear in terms of the transformed explanatory variable, x prime equals the exponential of x. Transformations don't need to be smooth functions. They can include piecewise, step, or other non-continuous functions, such as binary variables, to capture various types of nonlinearity in the data. The output variable can be a function of several input variables. Let's see what happens when those inputs interact with each other. Consider the model y equals beta 1 x1 plus beta 2 x2. Here, we expect y to increase by beta 1 per unit increase in x1, with x2 held fixed. However, the marginal rate of increase in y might differ for high values of x2 compared to low values. To capture this, we can create an interaction variable, x3, equal to x1 times x2, and add it to the model with its own coefficient, beta 3. Taking the partial derivative of y with respect to x1, we get beta 1 plus beta 3 x2. The rate of change of y with respect to x1 is now a function of x2. That is the interaction effect. One more note. We can use statistical tests, such as t-tests, to check whether the interaction variable is significant. If it is not, it may be redundant and can be excluded. But the hierarchical principle asserts that if an interaction term between two variables is included in the model, then both variables, called the main effects, should also be included, regardless of the statistical significance of their coefficients. The reason is that if the interaction term is related to the response, the exact significance of the main effects is less important. Excluding them can also distort the interpretation of the interaction due to correlation with the interaction term. Statistical learning has two main goals, prediction and inference. Let's start with prediction, which aims to accurately predict the output y based on the inputs x. We can model prediction with y hat equals f hat of x. Here, y hat is the predicted outcome, f hat is the fitted model, and x is the set of input variables. The focus is on the quality of the prediction, rather than on understanding the underlying relationship between the variables. F hat is considered a black box if we do not need to know or understand how the inputs x are transformed into the output y hat. The inputs go in, the predictions come out, and we care only about the accuracy of those predictions. Many machine learning algorithms, like neural networks and random forests, are often treated as black boxes because they provide accurate predictions without easily interpretable rules. How good can our predictions get? The expected squared difference between the actual and predicted values can be decomposed into two components, reducible error and irreducible error. Here is the decomposition. The expected squared prediction error equals the squared difference between the true function f and our estimate f hat, plus the variance of the error term epsilon. The first term is the reducible error. It arises from the difference between the true function and our model's approximation. We can decrease it by improving the model, choosing better predictors, or using more sophisticated techniques. The second term is the irreducible error. It comes from the inherent variability in the data and cannot be reduced by any model, no matter how complex or well-tuned. There are always factors affecting the response that are not in the model, and natural randomness will still cause deviations even with a perfect model. Let's put numbers on this. Suppose we predict students' exam scores from study hours, x1, and practice tests taken, x2. The true function is 50 plus 2x1 plus 3x2. Our fitted model is 48 plus 1.8x1 plus 2.9x2. The variance of epsilon is 25. Consider a student who studied for 10 hours and took 3 practice tests. First, evaluate the true function, 50 plus 2 times 10 plus 3 times 3, which is 79. Next, evaluate the fitted model, 48 plus 18 plus 8.7, which is 74.7. The reducible error is the squared difference, 79 minus 74.7 squared, which is 4.3 squared, or 18.49. Finally, we add the irreducible error, which we are given as 25. The total expected prediction error for this student's score is 18.49 plus 25, which equals 43.49. So what is this number really assessing? For a realized student, y minus y hat is the gap between the actual and predicted exam scores. 43.49 is the expected squared size of that gap, accounting for both the model's error and the unpredictable error epsilon. Because the gaps are squared before taking their expectation, 43.49 is measured in squared points. Taking the square root returns us to the original scale. The corresponding root mean squared prediction error is about 6.6 points. Because the irreducible variance alone is 25, even a perfect model would still have a root mean squared prediction error of 5 points. The second goal of statistical learning is inference. Inference aims to understand the relationship between the input variables x and the output variable y. The focus is on interpretability and on understanding the form of the function f. Inference has 3 specific goals. First, identifying associated predictors. Typically, only a small fraction of the predictors are associated with the response. Second, understanding relationships. We want to quantify how changes in each predictor affect the response, whether positively or negatively. And third, assessing model form. We need to decide whether the relationships are linear or something more complex. For inference models, f-hat cannot be a black box for 3 reasons. Transparency. It is crucial to understand and explain how each predictor affects the response, and black box models obscure this. Interpretability. Inference relies on interpreting model parameters, which black box models do not provide. And explanation. Inference aims to explain observed data patterns, which requires clear, interpretable relationships between variables. So when do we model for prediction, and when do we model for inference? Let's compare the two side by side. Modeling for inference is appropriate when the primary goal is to understand the relationships between variables, make causal statements, or test specific hypotheses. Inference focuses on interpreting the coefficients of the model to determine the effect of each predictor on the response. On the other hand, modeling for prediction is used when the primary objective is to accurately forecast future outcomes or classify new observations. This approach emphasizes the overall accuracy and generalizability of the model to new data, rather than the interpretability of individual coefficients. Consider predicting the price of a house based on size, location, and age. For prediction, we might use a complex model like a neural network. We don't need to understand how each feature affects the price. We only care about accuracy. For inference, we would use a simpler, interpretable model like linear regression to understand how much the price increases per square foot or how location affects the price. In some situations, we need to model for both inference and prediction simultaneously. In that case, we can use interpretable models like linear regression and validate their predictive performance against more sophisticated models. Combining insights from both approaches leads to more informed decision-making. A parametric method assumes the data can be modeled by a particular distribution characterized by a fixed number of parameters. It's called parametric because we estimate a set of parameters. Parametric approaches follow a two-step model-based process. In the first step, we define the functional form of the model. For example, a linear model can be expressed as f of x equals beta 0 plus beta 1 x1 plus beta 2 x2 and so on up to beta p xp. The x's are the predictors and the betas are the parameters of the model. In the second step, we fit or train the model to the data to estimate those parameters. One common method for fitting a linear model is ordinary least squares, but there are many ways to estimate parameters, covered in later videos. For example, we could model income as approximately beta 0 plus beta 1 times education plus beta 2 times seniority. A linear fit like this may not capture the true function exactly, but it does a reasonable job of capturing the positive relationship between education, seniority, and income. Let's summarize the characteristics of parametric methods. 1. They have a fixed number of parameters. 2. They rely on model assumptions, often that the data follows a specific distribution. 3. They tend to be simpler and easier to interpret. 4. The primary task is estimating the parameters, usually with maximum likelihood estimation or least squares. And 5. They are computationally efficient because the number of parameters does not grow with the size of the data. Flexibility refers to a model's capacity to fit a wide variety of shapes and patterns in the data. Flexible models can capture complex, nonlinear relationships between the predictors and the response, but they also carry a higher risk of overfitting and may require more data to estimate their additional parameters reliably. On the left, a simple model captures the underlying trend in the training data without following every fluctuation. On the right, a highly flexible model passes through every training point. Overfitting occurs when a model is too closely fit to the specific features of the training data, including the noise, which leads to poor generalization to new, unseen data. An overfit model has low training error but high test error. It captures noise and random fluctuations rather than the underlying data distribution, resulting in poor predictive performance on new data and misleading conclusions about the relationships between variables. Remember, noise is the random variability or error present in the data, arising from measurement error or natural variability. It represents the irreducible error, which no model can capture, and it limits the accuracy of predictions. A non-parametric method does not assume a fixed form or structure for the underlying data. Instead of having a predetermined number of parameters, non-parametric models let the data dictate the model complexity. This makes them well suited for capturing complex and unknown relationships. Non-parametric methods have three key characteristics. First, flexibility. Because they don't assume a specific functional form, they can adapt to a wider variety of data patterns. Second, data-driven complexity. As more data points are observed, the model can become more detailed and accurate. And third, no fixed parameters. Unlike parametric models, the number of parameters can grow with the data. There is a trade-off between flexibility and interpretability. Restrictive models, such as linear regression and the lasso, are more interpretable and useful for inference. Highly flexible methods, such as bagging, boosting, and thin plate splines, are useful when the goal is prediction rather than inference. Flexibility might seem preferable, but it can lead to overfitting, resulting in less accurate predictions. So less flexible methods can sometimes provide more accurate predictions by avoiding overfitting. Statistical learning methods fall into two broad camps: supervised learning and unsupervised learning. So far, we've discussed supervised learning techniques. Supervised learning uses labeled data, where each data point is associated with a response measurement, also known as a dependent variable. This response provides a target that the algorithm aims to predict or classify based on the input features. Common supervised algorithms include linear regression for continuous responses, logistic regression for binary classification, and decision trees and random forests for both. The majority of the exam SRM syllabus tests supervised learning. Unsupervised learning, in contrast, deals with data that has no labeled responses. The challenge is to infer the natural structure present within a set of data points, discovering hidden patterns, relationships, and groupings. Common unsupervised algorithms include k-means clustering, which partitions the data into k distinct clusters, hierarchical clustering, which builds a tree of clusters, and principal components analysis, which reduces the dimensionality of the data while preserving as much variability as possible. Unsupervised learning is discussed in detail in Learning Objective 5. Let's distinguish between regression and classification. The key is understanding the types of variables involved. Variables can be characterized as either quantitative or qualitative. Quantitative variables take on numerical values that represent some measurable quantity. They can be continuous, like height, weight, or temperature, or discrete, like the number of children in a family. Problems with a quantitative response are typically known as regression problems, using methods like simple linear regression and ridge regression. Qualitative variables, also known as categorical variables, take on values that represent distinct categories. They can be nominal, purely categorical without any order, or ordinal, with a defined order but no meaningful intervals. Problems with a qualitative response are typically known as classification problems, using methods like logistic regression and decision trees. Here's the key point. The response variable plays the most important role in selecting a statistical learning method. The predictor variables are less important in model selection. And keep in mind that many methods, such as decision trees, generalized linear models, and k-nearest neighbors, can handle both quantitative and qualitative variables. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.